We love you, Mr. Lake.
Mr. Lake's Wild Ride. Okay, careful, I don't want that recorded. All right, now, my favorite ride at Disneyland, it's not California Screamin'. It's Mr. Toad's Wild Ride. I don't know why I like it. I go on Mr. Toad's Wild Ride, I go, that's the best ride at Disneyland. Okay, and just because it's so unbelievably weird. I don't know. So I thought, well, if I could design a roller coaster or a ride, what would it be? Well, people would start on the ground. And then it would have one little car like this with two people in it, and they're all excited. See, their hands are up in the air. And they're going to be on a track. And the track goes all the way up to the top. Then it goes all the way down. Then it goes up a little hill. Then it goes down. And then all the way at the end there's this brick wall right here. And that's it. So now, if you think about it here, how much mechanical energy do they have here at the bottom? Well, let's define, we always have to define where gravitational potential energy is 0. And it's always logical to pick the ground, or usually. So U equals 0 right here. And they're not moving yet, right? So what else is 0 if they're not moving? K equals 0 at the bottom. So how much mechanical energy do they have at the bottom? 0. Now, we have to get them to the top. So here they are at the top. Now, how did they get there? No, there's no magic here. Well, there is some magic. Okay, but somebody, have you ever been on a roller coaster and they haul you up to the top? Well, how'd they get you up to the top? Because somewhere in here there is a chain that's looped around a pulley or something like this, and it comes down here, and here's another pulley, and it goes up like this, and connected to this pulley is a motor or an engine or something like that, and this is connected to the grid, and somewhere there's a power plant that's producing electrical energy, goes through the wires, goes in here, and it does work. Somebody from the outside had to work. Now that applied force that comes from rotating this chain that pulls you up is a non-conservative force, in that it's changing your mechanical energy. Obviously your mechanical energy up here is not 0. Let's call this big H, because that's my biggest height. Well, my mechanical energy up here is mg big H, right? So somebody had to change my mechanical energy, and it was done by an applied force. The applied force got energy from this electrical energy, haul your fannies up to the very top of this hill. Okay, then they release you. Okay? And so what happens now is that what force, as they're going down the hill, here they are going down the hill, here's their arms or hair swishing back, they're starting to go fast. What force is acting on them right there that's doing work? There's no applied force anymore. We're going to pretend, and here's the magic, we're going to pretend that there is no air friction or rolling resistance of any kind. There's no friction in this problem. This is a frictionless roller coaster. So the only force doing work is the component of gravity that pulls them down. Now this is a curved track. So I can't use, I drew it pretty straight. I should have made it like all curvy and stuff, because what matters here is that the only force doing work is gravity, and therefore mechanical energy in this situation is conserved. And so I can say, well, what kind of mechanical energy do they have down here at the very bottom? Well, their gravitational potential energy is 0, but what have they got? What kind of energy do they have? Kinetic energy. And then they go up this little hill. Well, when you go up the little hill, you slow down, right? But when you get to the top of that little hill, you still got some speed left. Okay. Then you get down here. Okay, this is where it gets exciting. They still have, they're going the same, because this is frictionless, they're going the same speed here as they were here, because they have the same amount of mechanical energy. Now I don't want, I want to avoid some lawsuits, okay? Especially with Caitlin here. So what I'm going to do, I'll tell some lawyer jokes later. All right, there is. Oh, sorry. There is a spring here, a magical frictionless spring with a spring constant of K. And so this spring will get compressed. Now, here's the thing. In this system, I'm going to make this whole thing my system. Of course, excluding the electrical generator and stuff. From here on, this is my system. It involves the earth, the spring, and the roller coaster. And the only forces doing work are the forces of gravity and the force of the spring. And therefore, we can say these are conservative forces, so therefore we can say that the mechanical energy here is equal to the mechanical energy here, is equal to the mechanical energy here, is equal to the mechanical energy when it compresses the spring and stops. E equals E equals E equals E. Isn't that exciting? Now, what you have to do, here's the killing part. Here's the part that makes a super powerful problem-solving technique. Let's say I want to know, let's give this little h, okay? Let's say I want to know how fast I'm going right here. So E equals E. Well, what is E here? E equals mgh. But that's going to be equal to the E I have here. Well, what kind of energy do I have right here? 1/2 mv squared. This gives me an equation I can use to solve the problem. I don't know what the problem is. Maybe it's how fast am I going given this height? Or maybe how high was this hill if we're going this fast? By the way, what doesn't matter? What doesn't matter in this particular problem? The mass. Well, what about this? What if I want to know how fast am I going at the height up here? Well, E equals E. So I can say, well, mgh equals, well, what kind of energy do I have here? Well, I've got some height, so I've got gravitational potential energy, and some of the energy is stored in its motion. It's moving. 1/2 mv squared. So look, this idea of conservation of mechanical energy has now given me an equation I can use to solve the problem, whatever that problem happens to be. Like, how fast am I going, based on these heights? Or how high do I have to make the little hill to go this fast at the top of the hill if I started from this height? I mean, you have to be given enough information to solve the problem. But if you're a roller coaster designer, this is an equation that you'll want to use. Because you don't want this speed to be so great that you're going to fly off the track. Or maybe you do, but... Now, over here, you've got a spring that will compress. So how much will the spring compress? Well, it depends on its spring constant, but it also depends on how high this hill was to begin with. E equals E. So mgh equals 1/2 k x squared, where x is how much the spring got compressed. Now, you're going to have lots of problems that involve gravity and springs, and we're going to assume there's no friction, no applied forces. And so what you can say throughout the whole problem is E equals E. And then you look at, okay, where is the energy over here, and where is the energy over here, or over here, or over here? Wherever it is, you set those mechanical energies equal to each other, and you solve for the unknown. And here's what's so powerful about it. It doesn't matter what happened in between. Okay, look, I'm going to make this ride really wild here, okay? And let's say my goal is to figure out how fast I'm going right here. Well, watch what I'm going to do. I'm going to change my wild ride. We're going to go down here, and then we're going to put in a loop-to-loop right here. Oh, there we go. All right. Now, not sure this is going to survive. All right, but hey, but here's the idea. It does, this loop-to-loop has no effect on how fast you're going to go anywhere else on the track. What happens in between here and here doesn't matter if the only forces doing work are springs and gravity. That's conservation of mechanical energy. A really important idea. Okay. Last thing, if there are now watch this. This is why, and this is not in your book, so I'll finish on time, I promise. The work done by a non-conservative force is equal to the change in mechanical energy. Well, in the second half of the problem, over here, from here to here, there are no non-conservative forces. So the work done by a non-conservative force, what is it going to be if there are no non-conservative forces? This is zero. So if all your forces are conservative, the work done by the non-conservative forces, which don't exist, are equal to zero. So 0 equals delta E. Oop, delta E. Okay? Well, if delta E is equal to 0, that means that E initial equals E final. So that's why this contains everything. If you can grok this equation and apply it to, it'll solve all your problems. Okay? Anyway, that's enough for today.